Hi everyone. So let's get started with lecture 5. So in this lecture we're going to be looking into the notion of duality and how we can use it in the context of linear programming. So we're going to talk first a little bit about how do we formulate um, dual problems and their relationship with the original linear programs we've been talking about, which we'll call from now on primal problems. And then we'll look into a little bit some important theoretical results associated with duality. Then I'll give you a sort of a geometrical interpretation of what duality means in the context of linear programming. And then we'll look into two practical applications of duality, which is looking into dual values as marginal values, and then the dual simplex method, which is a variant of the simplex method that is been found to be quite often more efficient in terms of computational performance. It's pretty much one of the most used forms of simplex method in professional implementations of the simplex method. So this first video is about the formulation of duals. Right. So once again, let's start with our traditional problem with n variables and m constraints. Written like so standard form right here. You're gonna notice that we're gonna be switching quite often in terms of whether we write these as equalities or inequalities, and just because we're trying to be general when it comes with the formulations. So I'll try to point it out, but also pay attention that sometimes this is going to keep changing for this part of the lecture. So this is what we're going to call our primal problem, because we're going to be talking about dual relationships. So basically, one way of thinking about duality is it's a frame. You can think about it as a framework that allows you to remove constraints from your problem. And the reason why you want to be doing such is typically related with potential benefits in terms of computational performance. So you might be making your problems, say, easier to solve, or you might expose some somewhat of properties such as make it separable, or that then you can solve with parallel computers. And many other. We're gonna see a few applications of duality also next class and then later in the course. But basically, what you're trying to do is to remove this constraint from the feasibility set and start treating it as a part of your objective function. And we call this this idea of removing the constraint and moving it to the objective function, then having it represented by a penalty system that gives you some sort of penalty whenever the original constraint is not satisfied, is what we call a relaxation, because we are relaxing constraints from the feasibility set. So what I do is I replace this condition ax equals b with a violation penalty, which is given by such. And basically what this is going to do is whenever b is not equal to a equals to x, I'll have this weight p that in the context of linear programming is referred to as price p, that will make sure that I get penalized by deviations between these two. And of course, this is because this is not restricted in sign by any means. It can act in a way that whenever this is positive, then this is also will be positive, and whenever this is negative, this will also be negative, because in both cases it represents a positive penalty in a minimization problem. Bear in mind that if this is a maximization setting, then you have these things with opposite signs, such that you're removing value from your objective function would be maximizing. Okay, but that doesn't change anything in terms of the results we're gonna develop. So basically what we're trying to find is what are these p's that once they are here, they correctly enforce this term to go to 0 by making these two things match, meaning that I found a solution that is feasible to my original problem p, but notice that would be possible solving a problem that has no constraint other than the negativity of the axis. And this is something we're not going to discuss much in the context of linear programming, but when you look at general optimization problems, like we do in linear optimization, we'll see that typically solving unconstrained problems is easier and under our methodological standpoint than having to solve problems that are constrained, because unconstrained problems can then be generalized to the set of reals, and you don't need to check against feasibility. So duality is useful as a mechanism for such. So let's call this x bar the solution of my original problem P. This is one of the main properties that dual problems have, that we're going to be exploiting over and over again. And it relates to the fact that whenever we look at this problem that I'm calling GP, which is basically solving my relaxed version, my unconstrained problem, my penalty version for a given set of P's, it consists of minimizing this problem, which if I do in terms of x, it gives me a solution that is less or equal than this, because this in principle is just a x that I obtained when I optimized P. Okay, not necessarily optimal for this, but I do know, because this was obtained for the original problem P, the solution has to be feasible, meaning that this term is going to vanish, which returns me this. So now if I stare at the right hand side and I stare at the left hand side, and bear in mind this inequality that appears in the middle, this is telling me that whenever I solve a dual, I'm getting a lower bound to my original problem. So it's almost like this unachievable bound. It's coming below from the minimum of my original problem, right? And the reason why it's unachievable is, you can think of it, it's just because you're removing constraints, right? So in that sense, it's like such. And if this is a lower bound, the first thing that comes to mind is, if you're trying to use that in a setting where you want to use this problem to solve the original problem P, you're probably going to be interested in having these bounds, these lower bounds, that are as tight as possible. In other words, what you can do is looking at this problem and then maximize this in terms of P, trying to push this lower bound. So one picture I like to draw is, you are minimizing. This is your Z star somehow, which is the optimal value for your problem P. And what you're doing with your dual is finding solutions that are living here, because they are lower bounds. So let's call this ZD. That's an ugly as Z. Let me do this. There you go. Here for a given P, right? And then what we're trying to do is to make sure we push this towards there. So that's what the maximization in P is trying to do with this bound. Notice that this is a weird problem, by the way, because this function g, represented as a function, is actually in itself a minimization in x. And then there is this outer maximization that is happening on P. So it's like a bi-level sort of setting, or a bi-optimization. Bi-level because you have two levels of optimization. So, and that can be confusing sometimes. But the cool thing is that this is unconstrained as well in P, and it's gonna give me my tightest possible bound. Tightest bound is good, but for all this to be really useful, for that to be meaningful as we expect, the main important thing that we have to observe from this is that, when can we see this? So when I solve this problem and find when I solve this problem and find my P bar, when is it such that that P bar is going to actually give me the same value of my original problem, which means then I'm actually solving the problem I wanted to solve before. And that's what duality theory evolves around. I mean, it gives you the theoretical setting to guarantee that this is the case. And that's what we're going to be exploring this week, in the next couple of videos as well. So just a quick remark is that a duality can be seen as a framework, in a sense, is a collection of techniques. in which you can replace constraints with equivalent representations. So one equivalent representation is this pricing idea with a penalty. There are other ways of representing constraints, as we're going to see later, much later in the course when we talk about bundle decomposition and column generation. We're going to return to that then. And it's basically why you're interested in that is because you're interested in developing alternative solution strategies. And in terms of optimization, a lot of the strategies or the methods that are associated with finding optimal solutions for constrained and unconstrained problems, but mostly constrained problems, is by means of a duality result. It's based on some sort of duality development. So here is something related to how do we formulate dual problems. So if we think about the definition of the dual problem D, which is represented by this, we can see that my problem so this is we can think of this problem that this is the inner problem in which my P has been already decided to some extent. So this problem is only on X, and because it's only on X, this term here doesn't play any role other being a constant. So I can get this term and move outside. Now these two terms depend on X, I can put them together. And now if I stare long enough to this, one thing becomes clear to me. Regardless of, the P that is coming in, I have, in order for this to be bounded, so this doesn't go to infinity and beyond, this thing cannot be negative. Because my X is constrained to be non-negative, so my X can be positive. And remember that this problem is unconstrained now. So if this thing is negative, I can make my X go to infinity, and this is going to go to minus infinity, meaning that the problem is unbounded. So to guarantee boundedness, I have a dual feasibility condition, if you wish, that says that this thing has to be such. And because this condition is basically everything I need from this sort of inner part, I can get rid of this X minimization to some extent, or in other words, pose the dual problem itself as a linear program. I'm trying to find a P that maximizes this thing, and the way to maximize this thing is guaranteeing that this term will not be negative, because otherwise this is unbounded. If you think about what I just said and write it as a linear program, you will obtain something that looks like this. I'm trying to maximize this and guarantee that this doesn't become minus infinity. In other words, what I want to make sure is that this is greater than or equal than 0, which can be represented like this. And I want to maximize this term in terms of the P. And there we go. So that means that now you can actually write your dual as depending only on the set of dual variables P. Which is, and this problem is the dual, is the dual problem, if you wish, for your original primal problem, which was minimize C transpose X with AX equals B, X greater than or equal than 0. Okay? So that's the dual problem for your primal problem P. And that's just that. So for every primal problem, you can formulate an equivalent dual. And the only thing that will remain is that to show whether when actually is the case that these two things will match. Okay. So of course the formulation of your dual is dependent on the formulation of your primal. But these things they kind of have predefined sort of relationships. Let me give you one example, and then we'll generalize it. So thinking about now that this is LP formulation for duals, I'm posing a different primal now. So now I'm posing up my primal as a greater or equal than, and I'm not assuming any constraints on non-negativity constraints on my variable x's. So I'm just assuming that x can be any variable in reals, in the space of reals. Okay? So let's see how my dual, the formulation of the dual, the LP formulation of the dual would change if my primal was written differently. So we know that we can reformulate this into an equivalent form in which we just add slack variables there. Slack variables with negative sign that are constrained to be non-negative. Okay. So if I look at this constraint here, what changed now is that this left-hand side kind of looks like this. I have AX and minus identity multiplying S to represent this thing. Remember that this is a collection of constraints as big as the number of rows in A. Okay, right. So if my dual is originally like so, and I do exactly the same reasoning as before, I write this here. I write my G of P, but now with my new constraint and so on and so forth. If I do exactly the same chain of thought, I get to the following conclusion. So I get into the situation that to guarantee boundedness, I have this being forced for the whole set of constraints, and then I have this another one down there being forced. And these are coming from the fact that I have these two constraints there. It's not hard to do that. All you do as an exercise, you just derive, once you have your constraint written like that, you go on and derive exactly the same conditions we saw before. And because now we have these two conditions, you can see that this first part here is telling me that P transpose A less or equal than C. The second part is saying that minus P less or equal than 0. And then I have this third one saying that C equals to P transpose A. So basically this first part here can be ignored because this is sort of stronger, right? So meaning that this becomes this constraint there. And then the second part, is the only thing that has been said about P. So this one can becomes P greater or equal than 0, or the other way around, minus P less or equal than 0. So basically, if you look at this now, the only difference is that my constraint changed here, and now I had a new sign there. So regardless of the formulation of the primal, you can find a LP formulation for your dual, but it might change depending on the original structure of your dual. And you can always work out what the formulation is by following a similar argument. But to make life easy, or easier at least, what I'm giving you is like this general rules for converting primal problems into dual problems. So for that, we'll assume a canonical form. So this is kind of perhaps the first time we're talking about canonical form. So a canonical form is that form in which we presume a minimization greater or equal than constraints, non-negative variables, which is different from the standard form, or could be made a standard form if we went and added slack to become equalities, to turn these into equalities. But the canonical form is saying is that this is, I don't want to say the word standard, but it's this reference form that we use to derive, say, duals, for example. So our canonical form is the form which, assuming our problem is written before we do, dual conversion. So if our primal problem is written like so, our dual also comes in a canonical form, and then a canonical form is a maximization with less or equal than constraints, non-negative variables. Okay, so this term is this problem is the exact dual of this, and this is different than the last one because we're adding the greater or equal than constraint, which has an impact of changing this into a lesser or equal than. And you can also work it out to see why is it so. So in order to make life easy, I'm presenting you this general the conversion table, which basically tells you what you need to do to go from a primal to a dual and vice versa. So in a way to read this table is the following. You have first to identify whether your primal problem is minimization or maximization. So if you have a primal that is maximization, you read from right to left. If you have a dual primal that is minimization, you read from left to right. So like in our case, assuming that our problem came in the canonical form, we are reading a primal minimization, so it's from left to right. And basically what it's telling us is that our dual is going to be a maximization. Our independent terms, they're going to become objective function coefficients. So these are the independent terms. Our objective function coefficients, they become independent terms. So objective function coefficients become independent terms. The ith row of the constraint coefficient becomes the ith column of constraint coefficients. So this matrix here appears transposed, right? And likewise, the columns become rows. And then in terms of constraint, each greater or equal than constraint you have in the minimization problem is going to become a variable that has as feasibility condition being non-negative. So because this was a minimization with a greater or equal than constraint, this yielded a variable that has a non-negativity condition. And that's what it's saying here. If that were a less or equal than constraint, then you will end up with a less or equal than variable. And if it was an equality constraint, non-constrained variable. And for each variable you have in your primal problem, it's going to become a constraint in your dual problem. So a greater than equal variable becomes a less or equal than constraint. So be careful because it swaps. A less or equal than variable would become a greater than equal than constraint, and so on. So you can use this table to do any sort of formulation conversion you need. And this table is basically a summarizing all possible different variations of formulations we just seen. So just a few brief remarks is that a dual of a dual in linear programming is always the primal. So you kind of cycle the dual of the dual is the primal, and the dual of the dual of the dual is the dual, and so on and so forth. And that property is called self-dual. Some problems have this property. Some types of optimization problems have this property, and linear programs definitely have, which is great for us. And another thing, whenever you have to do transformations in your formulation, you end up with equivalent duals as well. So these are the formulations we use to convert things from canonical to to standard form, or to when we have a variable that's say negative or real, not constrained in sign. We use these auxiliary variables, or even when we're removing redundant constraints, you see that we always end up with equivalent formulations for our duals. So let me demonstrate it by example. I have this trying to show the equivalence of these formulations. So basically, here is my primal with a variable that is restricted in sign. And if you go and use the table we just seen to formulate the dual, this is minimization with greater or equal than constraint. So that is going to get me a greater or equal than variable. And I have one variable that is restricted in sign. So that variable is going to yield a equality constraint. And how do I see that constraint? Well, for x, the independent term here is the C there, the objective function value. This matrix is just a transpose, but I'm flipping these two. That is equivalent to A transpose P. And finally, for that, my independent term goes into the objective function, and the variable associated with this constraint is P, so it's like that. So you always see this, row becoming column and column becoming row. Okay. So now suppose that I don't like greater or equal than constraints, so I'm gonna convert this into the standard form by making it equality, and I get something that looks like this. So now I have my slack variable here with 0 coefficient in the objective function, because that's what we do with slack variables. And my variable is still constrained to be real, but my slacks are non-negative. Okay. So now what is happening here is the same story, basically. I have one constraint, so I get one variable in my dual, my P, and because my constraint is equality, my variable is restricted in sign. For each variable, I get a constraint. So for the variable x, which is real, I get a constraint that is equality. And for a variable s, I get a less or equal than constraint because it's greater or equal in my primal. So two constraints. Okay. And once again, the terms in this constraint is the terms associated with the variable x. So the c is there and the a is here. And the terms in this constraint associated with the variable s, which basically is this coefficient here, and this term, independent term there. Okay. And yeah, and then if you look at this is exactly this, right? Because you have this condition combined with this condition. And if you multiply by -1, this just becomes that. Okay. And last but not least, suppose now instead of, just not do this, but I want to get rid of the fact that this is constrained to be real. So what I'm doing is I am adding two non-negative variables and saying that x is actually the difference of them two. So likewise, I just do the distribution and you can see that I'm getting exactly the same. Now I have two variables, so I get two constraints, and then one constraint is going to say less or equal than, the other constraint is going to say greater than or equal than, and when you compare this with this, you see that it's exactly the same once again, because you're merging these two constraints. So this is basically to say that you can always rely on that table as a guidelines to derive your duals, regardless of the formulation you have for your primal problem. And you're always going to end up with equivalent formulations, even if you apply reformulations. All right. Let's stop here for this video. And in the next one, we're going to look into some theoretical aspects of duality. See you in the next video.